welcome to our Friday. Hopefully you have a somewhat restful weekend ahead of you, or productive weekend, whatever it may be. I hope to do both, be productively relaxed. So today we're going to dive into exponential functions. We'll highlight some of the things of how we use exponential functions with algebra. However, we won't be working through a lot of algebraic manipulations with this yet. We're kind of going to use limits, all your favorite, right? But we're going to use it in a slightly different application that might help limits make a little more sense. So the good news is that we can understand this lesson without understanding limits. However, the way they use the limits, it might help us understand limits from before. And then the thing is we're not really actually doing any calculus with it, although I'm going to introduce a little calculus by observation. We do that in a future section, which is coming up pretty soon. But we're going to look at this exponential, why it's such an important function for us to deal with, or to understand. We'll look at logarithms, which are the inverse. So as we understand this, we're going to hopefully help us understand what that logarithms is just the inverse. So it's switching the input and the output. And then we'll do some calculus with it. And again, most of the calculus we'll see is sort of, they will develop it with limits. However, we just need to remember the last part of it. This derivative of this equals that. And we'll be able to use it without having to go through the limit process, which is especially helpful with logarithms because it's like a 2-page thing and I can never get it right. But I can remember what the derivative of a logarithm is. That I can do. And you'll see when we get there, it's pretty simple. It's pretty straightforward. So actually I didn't update this, but we are now here at section 3.1. I did post the review recording that we did from Wednesday, so that's there. We'll do 3.1, and then again, we've got a little ways to go, but by the time we get to 3.7, looks like we don't have a 3.6, so there's a section we skip in there. But by the time we get to 3.7, we will be working with exponentials and logarithms and their derivatives. Okay. And again, just sort of a reminder, what is a derivative? Slope, instantaneous rate of change. So it's a slope at a point, right? Without having 2 points, that's what really the derivative is and how we find it. Okay. So this is just a screenshot from module or chapter 3 from the books, and it's just highlighting we're going to do exponential, logarithmic, and then towards a part. I'm not sure if we'll get into I'm sure we'll get into the inverse trigonometric functions because there's some things we deal with it. But today we're going to focus on this part, exponential functions. And again, your knowledge of exponential functions from algebra will be sufficient for what we need to do here. We're going to throw in some concepts using limits to kind of say why certain things work that we sort of probably just took for granted without too many questions. So what does an exponent mean? So this is the first thing, and what we want to look at is that actually it means different things depending upon what the exponent is. The easiest one to understand is if the exponent is a positive integer, so numbers like 1, 2, 3, 4, 5. If it's a positive integer, then it simply means repeated multiplication. So something like if we have the example in the book, we have a to the third power, that simply means the base, whatever a is a number, multiplied by itself 3 times. A to the n power, n times. So that's kind of abstract. So that's all. If we have an integer value, that's really simple, and that's usually how, probably most of us, that's how we understand an exponent, just repeated multiplication. What we're going to see is if it's not a positive integer, then it actually has different meanings. Well, what if the exponent is 0? What does that mean to repeat multiplication 0 times? what does it mean to have a to the 0 power? It's 1. Some might, well, shouldn't it be 0? We don't multiply by anything. But it actually ends up being 1, mostly by definition. So this just is not a to the 1, it's just the number 1. So anything to the 0 power, except 0, I always put that side thing. If 0 to the 0 is like not really undefined. In fact, they call it the indeterminate form. So we just don't even touch that. But any other number to the 0 power, and where that comes from, we'll talk about the laws of exponents, but you should probably already know that. If you had a to the 5th power divided by a to the 5th power, how do we deal with those exponents? We subtract them, right? So this is, and looking at that, this is a number divided by itself, so it should be 1, hopefully. So a number divided by itself, we define, that's a sort of a definition of 1. We also could use exponent rules, and we get 5 minus 5, which gives us a to the 0. And that's why anything to the 0 power has to be equal to 1 to make these exponent rules, to make all of the other mathematics work. Okay, so that's another one. What's something else we might talk about that would be different? Talked about positive exponents, negative exponents. Good. Thanks for thinking in the same terms that we got a couple others that we could talk about. But what does a negative exponent mean? Now this, again, it's harder to think. Does it mean that negatives oftentimes means the opposite? Well, what kind of opposite does it mean? So if we have, say, a to the negative 5, what does that mean? Well, what's the opposite of repeated multiplication? Repeated division. That's how you want to think of a negative exponent. We're doing the opposite operation. So it's really, we're dividing by a 5 times. And when I put it down 1 over a to the 5th, in the denominator it's repeated multiplication, but notice I'm repeatedly dividing by it. Okay, so that's, we have a negative integer value. But there's other kind of numbers out there too, right? Not just integers. What's another kind of number that's not an integer? Rationals, fractions. So fractions are rational numbers. So what does it mean when we have an exponent that's a rational? And this is maybe a little harder to understand. Let's go with 2 over 3. But again, from algebra, we kind of look at these, and whatever in the denominator, that's a root. That's somehow what multiplies by itself, in this case, 3 times to give us a. The 2 in the numerator is just like a positive exponent. So we kind of break this up into 2 pieces of the numerator and denominator. So this we get to think of as, it's really just a to the positive 2 power, but it's all contained in a cube root of 3, or a cube root. And if the 4 was in the denominator, it'd be a 4th root or a 5th root or something like that. So fractional exponents mean we've got radicals. We're going to have a radical involved. Okay. The numerator is just treated as a positive integer, and then we got the radical. Now, if we have a negative rational, then we also flip it, right? Somehow we're going to have it in the denominator. So that could happen too. The last one, there's one other kind of number that we haven't talked about yet. Irrational. So we've got rationals, we also got irrationals. And these we just kind of say, okay, what is an irrational number? It's stuff like square root of 2, square root of 3. That's pi. Pi is an irrational number. You can't write it as a fraction accurately. We can get estimates. And its decimal equivalent, it goes on forever without repeating. So you can't really cleanly ever say you can really write that number because there's a couple digits you've left off. Actually, an infinite number of digits you've left off. So if you really think about it, then how can we do this? Well, what they do is they use limits and say something like, if we have a to the 1.7 and a to the 1.8, that what a to the square root of 3 is, because square root of 3 is a number that's between 1.7 and 1.8, it's somewhere in between those two. And again, you could take a look at that. They use limits to kind of talk about it. But we sort of use this squeeze theorem that it's something between these two, so we know it's going to be okay. And what we use is the limit as this number gets closer to this, so they actually define it. Maybe move. Actually, what do I want to do? I can't. Well, let me. Move that up, and then we'll go back to the slideshow so we can see it a little bit better. So they use the limit as the rational number goes towards x. Again, we don't have to think too much about it. It works. So we could, and our calculators would be able to handle this, so we can do a base to a rational number. Okay. But again, this is part of the textbook, just kind of wanting to bring in limit, this idea of limit again. But as far as exponentials, we kind of understand them. They work like we think they work. So they're really a smooth function. So let's take a look. There was some pictures. We could just look at pictures, but I thought let's go ahead and build this. So we could start with the function, and I'm going to do this as sort of the base function is 1 raised to the x power. It's a base raised to the x power. But does 1 raised to the x power, does that look like what we think of as an exponential function? No. It looks like a horizontal line, doesn't it? And in fact, it is, because 1 to any power is still 1. So this is kind of the dividing line of exponential functions. If the base is larger than 1, we're going to get one type of exponential function. If the base is lower than 1, we get another kind. So let's go ahead and see if we have it just a little bit bigger. So let's go with f of, well, it's g of x, I guess. G of x equals 1.2 raised to the x power. And we see now this is what we think of as an exponential. It's curving upwards. And this would be an exponential that has a 20% increase. So from algebra class, that 1 is like 100%, no change, it's constant. As soon as we got a 20% increase, 1.2, we start going up. Okay, so that's the dividing line. What would an exponential that's going down look like? 20% losing would be what? Yeah, it'd be 0.8. So we subtract the 20% from 100%, we got 80%. And what does that look like? It's going to be a decreasing. What do you notice about all three of these, though? What do they have in common? Particular point? They all go through the y-axis at 1, right? So that's kind of an important thing. And what we see is all, because no matter what the base is, when you raise it to the 0 power, what's the answer? 1. So that's what's happening there. X is 1 at that point. And then what's happening as we come out here, like square root of 3 is right somewhere between 1.8 and 1.9. It's here. And if you get onto any of these, you'll see that it's continuous. So it includes all the irrationals, all the rationals. You could also, anyway, they're all there. And we could get multiple other pictures. And the larger the base, if it's above 1, the larger the base, the quicker it increases. And below 0, between 1 and 0, you can't go below 0 because let's think of it. Negative, if it had a negative base and we raise it to any kind of a power, to a variable power, even powers would be positive, negative powers would be negative, and you get a discontinuous sort of graph. You get things that bounce around. It's not well defined. So we don't have negative bases. Our base has to be 0 or bigger than 0. Okay? So if you're less than 1, the further less than 1 you are, the steeper the decline, right? Let's see, I think that's how it works. So let's go with, we'll just go y equals, let's go with like a 0.2. So that's an 80% loss, right? Raised to the x. And that's a very steep decline. So the further away we get from 1 towards 0, the steeper decline we have. Going the other way, we get more increase. And so that's just kind of the feeling we get with these. Again, that's what's kind of nice about this section, is just kind of getting a feel for exponentials. I've got a couple questions in here on I think actually I only used one example because that's primarily we'll be going forward with that. Okay, so first of all, the other thing I wanted to talk about, and this is kind of why we use limits in mathematics, is to kind of make sure everything is clearly understood, that there are, like, again, a base raised to a rational exponent, irrational exponent, really doesn't exactly exist, right? Because there could always be one more decimal we put it, but we can get close to it. And we can get close enough that there's no holes in the graph. So what I wanted you to do is that last one we did about rational, irrational exponents, that was, if you go back maybe and look at it, it was a definition. They did that by definition. Well, what's a definition in math? It's just an explanation. It hasn't necessarily been proved, but it just says, we do this because it works. But we're not going to prove it or anything, you just trust us, okay? So that's when we're using definitions. Oftentimes, we just say, it has to be something, so we'll decide, and this is it. And who's we? I don't know, but I'm not part of that group. A theorem, though, is something that takes those definitions, and as we see, axioms, basis, and actually can prove that this is true. So when we talk about a theorem, that something has been proven, and then all these other things we use in math. Again, engineers probably are not real interested in all of these specific ones, and that's okay. I'm not all that interested either, but we'll talk about propositions, lemmas, corollaries, and then proofs. But those all have been, either we'll use a theorem that has been proved to do something. So there's various ways that they stand out, but the proof is actually giving the mathematical basis, okay? And a conjecture is something oftentimes we just think it might be true, but we don't take the time to prove it, because maybe it works. Okay, so we go with that. And then the axiom is just a basic assumption. Again, it could be wrong, but it's an assumption, okay? So now we're going to get to laws of exponents, and these come from theorems, okay? So these things have been proven. It's actually a theorem, right? It's been proved. We're not going to prove it ourselves, but we can take it. And again, these should be things that you're pretty much familiar with, that when you have the same base and you're multiplying them, and let's go backwards. So usually we sort of remember these the opposite way, that when you're multiplying two exponents, what you do is you put them on the same base and add them. You know, so the example is a second times a to the third. We end up with a to the 2 plus 3, which is a to the 5th. Okay, so these are just the rules from algebra that hopefully you're pretty proficient with. We'll spend a little bit more time when we get to logarithms, because oftentimes in algebra classes that's the part we get you to use them a bit, but then we go over it pretty quick. When we're dividing, and we kind of used this earlier, we're subtracting the exponents, so we use that to explain why a to the 0 power is actually 1, because it has the same exponents. When you are multiplying, or I guess this is sort of backwards, if you have an exponent raised to an exponent, then we multiply those exponents. And then there's sort of like, I call this sort of the distributive property of exponents over multiplication. So if we've got two things being multiplied, then the exponent goes to both of them. The same thing happens if we were dividing. If we had a over, well, we could do a over b and raised it to the x power. That would be a to the x over b to the x. Okay, so they didn't prove it, but it works. Okay, so that's the main things we just need to know how to use exponents. Questions so far? Is it feeling okay? Comfortable? Yes?
So, are we doing the same thing, like a exponent x plus y, and then the fourth one, is it the same, like, thing to do, do you see them? Do they get the same result?
So 1 and 4?
Yeah.
No. 1 is, well, wait. Because the bases are different. A and B have a different base. In the first one, the base is the same. Yeah, but you almost had me there. I said, yeah, what's going on here? Yeah, because the base is different. So sometimes you change just a little bit, and I hadn't thought of that. Good question. Okay, so now we're going to use, and this is sort of what we built up to, is we're going to use the most convenient base of an exponent. So we do 2 to the power is something that's been doubling. That gets used, because you're continually multiplying by 2. 3 to some exponent is like the tripling one, right? But there's one that's even more convenient, and it comes from this little formula, 1 plus x raised to the 1 over x. As you let x go to 0, that gives us a number, and again, there's probably a whole history about how they came up with this, but notice if you let x become 0, then this just becomes exponential to the first power, or sorry, to a base, and 1 over 0 would be infinity, so this is like, I guess if you were going to go to 0, it would be 1 to the infinity power, and what does that mean? So I want to show you that that by using limits, this number e, what does that mean? It means it's not going to infinity on either side. What's happening here, and why this is again, this would be an irrational number in itself. Let's see, we want to graph, what was the function? It was 1 plus x raised to the 1 over x power. What's all this stuff? I don't know. So what I'm going to do is kind of zoom in here. Well, I can go along here. Watch what happens as I actually get to 0. What is our answer? Undefined, which makes sense because if I plug in 0, it's not going to exist. So that value doesn't actually exist, but does the limit exist? If I look at this graph, does the limit of that point, even though the point itself does not exist, does the limit exist? I can get closer and closer and closer. There's only one little hole, that's when x actually equals 0. But I can get as close as I want. And what we can do here, let's insert a table. I'm going to turn this to x, and I'm going to turn this to f of x. And I'll show you as we get close to 0. So let's go to 0.1. How about 0.01? 0.001. And let me, it's kind of small, isn't it? Let's make it a little bit bigger. So we use this idea of limit as we get closer and closer. We're going to get closer and closer to this value we call e. To 2 decimal places, it's 2.71, or maybe it rounds up to 2.72. To 3 decimal places, I think we're 2.716 is pretty good. Again, maybe rounded up 2.717. But that's how we get this number e. It's not, it's sort of, and it gets you to feel, it doesn't really exist in a space, but we can get close to it. And that decimal expansion will keep going out, we'll get more and more accurate. And again, with engineering, we just figure how accurate do we need to be? That's where we stop. Maybe 3 decimal places, maybe 5, maybe 10, depends on what we're doing. But it's all an approximation. Okay, so that's the idea. Same thing happens with pi. It's an approximation. We get closer and closer, and that's what a big use of limits is. Okay, so just kind of this thing that happens. Okay, e itself sort of doesn't exist, but it's a number we can kind of get close to. But what's really cool about the number e, and I call it a number even though it's, where is it? I don't know. But watch this. let's change this. So that was this special function. As x gets towards 0, that's how they get the number e. But watch if we rewrite this as the exponential e raised to the x power. And so what was e approximately? 2.72 maybe. So watch what happens if we so if I did y equals 2 to the x, 2 to the x. Notice it is not quite as steep. If I do 2 to the 3, what would you expect to see? Oh no, 3 to the x, sorry. That one's actually a little bit steeper, but not too much, because 2.72 is pretty close to 3. So it's somewhere in between there. And again, we could sort of use limits and everything. But that's not the really cool thing about e. And this is going to, I'm jumping a little bit. We're going to see kind of, maybe it is not going to be as exciting later on, but let's make our excitement today. You've got to have some excitement, right? What do you think about the derivative of e to the x? Well, I'm going to do y equals, d dx, and with Desmos, that's actually going to take the derivative of it, and I'm just going to take the derivative of f of x, the function. I could put e to the x in there, but I'm just going to say, let's get the derivative of the function I put in there, and I'm doing that for a particular reason. So what do you see? That's the function. That's the derivative. That's the function. Does that mean that e to the x is its own derivative? That's exactly what it means. And so that's why it's so cool. So it's not only giving us a value, the function itself is also giving us the rate of change. The value it's at is also the rate of change at that point, which is just like, wow, this is like a very special number. Nothing else works that way. And the reason I did it this way, watch, if I change this base a little bit, I guess I have to change the whole thing. If I do 2 to the x, notice 2 to the x, when I take its derivative, is not the same thing. It's close, but not exact, right? Any other thing, it's going to be one way or the other. But e to the x is like so mathematically beautiful because it's its own derivative. And that's also going to cause us some of the greatest difficulty, because when we take its derivative, it's the same thing. What's the derivative of e to the x? E to the x. Well, which one's the derivative? They're both the same. So it's easy, but it's also a cause for confusion. Okay, but I just wanted you to see that if I graph them one on top of the other, we'll go back, change it back to e, that turn it on and off, right? That it is its own derivative. Okay, so that's why e is so cool. And that's why when we get to logarithms, we use the natural log of e as a very special logarithm, because it's got that connection. And things act pretty nice. Okay. So again, they use limits to kind of define the range. What happens as the limit as x goes to negative infinity, we kind of saw that the graph goes down to 0, and it's sort of a J curve. As x goes to positive infinity, it goes to infinity. So we can see that the y values, and again, we'll come back here, not to that one, this one. So it kind of just explains, yeah, as x goes negatively to infinity, the graph goes down to 0. As x goes to positive infinity, it just gets so huge, and it gets there pretty quick. Okay, so that's, again, something we probably used in algebra, but again, another use for limits to see what's happening at either endpoint of these functions. There we go. So let's look at an example. So again, we're back to limits, but let's think about what limits mean, because there's a few that they'll have you in here. How would we calculate this limit? We had a couple ways. We could use numerical values, so we could plug this into Desmos and look at a table as we get close. Well, I guess we can't get close to infinity, but we could see as we get to infinity what's happening. We could look at the graph. How about analytically? What do you think's going on here? we're not doing derivatives at this point. We're not going to go to the derivative. We're just wondering what's happening as x gets really big, what's happening to this function. Clearest way to do it is when we see the graph, we should be able to see that. So we don't, no chain rule thing, no product rule, no nothing. But what did we do earlier when we had like x polynomials? Well, 6 to the x is, when x gets big, what's going to happen? Y is going to get really huge, right? Because 6 to multiplied multiple times, that's going to get really big. So does 3, oops, let's back up. I got to turn my writing utensil back on. Come on. So this stuff, 3/8, that's really just kind of being added. Those numbers aren't going to matter. 6 to the x gets so huge, what is the only thing that matters? These are so big. We did this earlier with like x to the 5th. If they were both x to the 5th, what would we do? They cancel out, and it's just their coefficients, right? So let's see if that works here. So I would say this limit should probably be, as these get big, those will cancel out. It should go to -3/7, those coefficients. And again, I haven't proved it, but what I could do is go to Desmos, and Desmos will show us that, yes, that's indeed what is happening. So I'm 3 plus 3 to the 6. And again, when I use Desmos, I actually go ahead, make it a little smaller. So y equals 3 plus 3, 6 to the x. And, oops, not equals, 3 plus. There we go. Oops. Divided by 8 minus 7, 6 to the x. And again, what we want to see is when x, as we go to positive infinity, what's happening? Well, we see a y value as we get getting close to -4.29 pretty quick. Right, this -4.29. What is 3 divided by 7 anyway? 0.4 negative. Well, let's see. Where's my calculator? There it is. We could do 3 divided by 7. Oops, not that. 3 divided by 7, 0.4285, so that would round to 0.429, and if I made it negative, that's exactly what's happening there. So I can see graphically that's what's happening, so it makes sense, right? So that same reasoning we used with polynomials works with exponentials, maybe even better with exponentials. Okay, you could also do a table of values, but the numerator denominator gets so big after a while it won't give you values, because I went to like 1,000, and if you go a little bit over 1,000, then it didn't give me anything. So I think it just couldn't handle it anymore. Okay, so there'll be a few homework problems like that, looking at getting you back into limits. Yes.
So what if one of the 6x would be different, like if it was 6x over 7x?
Then that's going to be different. We don't have one in the homework like that, but I'll bet you then we could say which one is bigger, whichever is the bigger base. If it was in the top, it would probably go to infinity. If it was in the bottom, it would probably go to 0, because then we have that size difference. Just like if we had a different x, so if it was x to the 5th and x to the 6th in the bottom, right, then that's going to go to 0. So we looked at the size of those exponents. This time we're going to look at the size of the base. At least that's my conjecture. I didn't try it, but very good question. Yeah. We're up, and that's really it. We've got, I think, 7 homework problems in there, and again, there's no calculus in here, other than limits. But the limits are more just what's happening at infinity, so we can use Desmos and go through those. But it kind of gets us set up for this understanding of why we use e to the x so much. And then we go, one of the sections will actually prove that the derivative of e to the x is e to the x. but we don't, I mean, to me, that graph was proof enough. Seeing is believing. I saw it? Sure. So so this section will be kind of nice because we'll do this with logarithms as well. Spend a little time talking about logarithms in general, mostly from algebra perspective. Then we'll start using derivatives and see how to make the derivatives of these things and go from there. Kind of slow down a little bit, which is good. Questions? Have a beautiful weekend. Getting into the nice part of the weather, right? Not too hot. Still got sunshine. Oh, I forgot to change this, but. Sure.